For over a century after Albert Einstein published his theory of general relativity, black holes existed only as mathematical equations on blackboards. They were defined as cosmic traps of infinite density so powerful that not even light could escape their gravitational pull. Because black holes absorb all light, astronomers around the world believed capturing a direct photograph of a black hole was physically impossible. Yet on April 10, 2019, humanity achieved the impossible, the reveal of the first direct photograph of a black hole's event horizon shadow. A glowing, fiery orange ring of superheated plasma surrounding a central dark abyss, supermassive black hole M87 star. In this 4K documentary, we explore the extraordinary engineering, global teamwork, and breakthrough physics behind this historic image. Welcome to the first image of a black hole and what it revealed. Part 1, The Challenge of Imaging an Invisible Monster. Black holes themselves emit no light, however, matter falling toward an event horizon is compressed and heated to billions of degrees. This glowing plasma forms an accretion disk, casting a dark shadow in the center, the silhouette of the event horizon. To capture this shadow, astronomers targeted Messier 87 *, a supermassive black hole located 55 million light-years away in the constellation Virgo. Although M87* contains 6.5 billion times the mass of our Sun, its immense distance makes it appear tiny in our night sky. From Earth, M87* appears the same size as an orange sitting on the surface of the Moon. According to the laws of diffraction, resolving an object that small in radio wavelengths required a single telescope as large as the entire planet Earth. Building a single-dish telescope 7,000 miles wide was physically impossible for human engineering. However, astrophysicists conceived an ingenious technique called Very Long Baseline Interferometry, or VLBI. By linking radio observatories across the globe and synchronizing their signals, scientists created a virtual Earth-sized telescope. This international collaboration was named the Event Horizon Telescope, or EHT. Over 300 scientists from 60 institutions across 20 countries united to attempt the impossible. Part 1 Summary: Imaging M87* required a virtual radio telescope with an angular resolution as wide as planet Earth. Part 2: The Global Network and Petabytes of Data. In April 2017, 8 radio observatories stationed at extreme altitudes around the globe pointed their dishes toward M87*. The network included ALMA and APEX in the Atacama Desert of Chile, the Submillimeter Telescope in Arizona, and the James Clerk Maxwell Telescope in Hawaii. It also included the LMT in Mexico, the IRAM 30-meter telescope in Spain, and the South Pole Telescope in Antarctica. Each observatory was equipped with ultra-precise atomic clocks using hydrogen masers to timestamp incoming radio waves to a fraction of a picosecond. Observing at a wavelength of 1.3 mm, the telescopes recorded gigabytes of raw data per second. The total volume of data collected during the observation run exceeded 5 petabytes, over 5 million gigabytes. This data volume was far too massive to transmit over the Internet. Instead, half a ton of helium-filled hard drives were packed into cargo crates and flown by commercial aircraft to central supercomputing hubs. Hard drives from the South Pole Telescope had to wait 6 months for the Antarctic winter to end before flights could land. The hard drives arrived at supercomputers at the MIT Haystack Observatory in Massachusetts and the Max Planck Institute in Germany. Supercomputers cross-correlated the signals from every dish pair, combining light waves collected thousands of miles apart. Computer scientist Dr. Katie Bauman led the development of the CHIRP algorithm to combine incomplete sparse radio data into a coherent visual image. To prevent human bias, 4 independent teams worked in strict isolation for over a year using different algorithms. When all 4 teams finally revealed their results in a closed meeting, every single team produced the exact same glowing orange ring. Part 2 Summary: Linking 8 global observatories produced 5 petabytes of data, yielding a historic mathematical image. Part 3, the April 10, 2019 announcement and M87* anatomy. On April 10, 2019, simultaneous press conferences were held in Washington, Brussels, Santiago, Shanghai, Taipei, and Tokyo. The National Science Foundation unveiled the image to millions of viewers worldwide, the first visual confirmation of a black hole. The image revealed a bright, asymmetric crescent ring surrounding a central region of absolute darkness. The dark central circle is the shadow of the black hole, approximately 2.5 times larger than the physical event horizon due to light bending. The surrounding ring is composed of superheated plasma orbiting near the speed of light. Notice that the bottom half of the ring is noticeably brighter than the top half. This brightness asymmetry is caused by relativistic Doppler beaming. Matter moving toward the viewer is boosted in brightness, while matter moving away appears dimmer. This asymmetry proved conclusively that the accretion disk is rotating clockwise relative to our line of sight. From the size of the shadow, astrophysicists calculated M87*S mass with unprecedented precision, 6.5 billion solar masses. M87*S event horizon spans 40 billion kilometers across, larger than the entire orbit of Pluto in our solar system. If placed at the center of our solar system, M87*S event horizon would extend far beyond Kuiper belt dwarf planets. Part 3 Summary. The M87* image confirmed a 6.5 billion solar mass behemoth spinning clockwise. Part 4, Scientific Discoveries and Einstein's Triumph. The primary scientific victory of the EHT image was the total validation of Albert Einstein's theory of general relativity. Einstein's 1915 equations predicted that a spinning black hole would cast a nearly perfect circular shadow surrounded by a Doppler-boosted ring. Alternative theories of gravity predicted distorted, oval, or irregular shadow shapes. The EHT image matched general relativity's mathematical predictions to within 10% accuracy. In 2021, the EHT collaboration published a second landmark image of M87* showing polarized light lines. Polarization revealed strong, organized magnetic field lines swirling around the event horizon. These magnetic fields act as powerful funnels, launching twin relativistic plasma jets extending 5,000 light-years across space. M87*S relativistic jets blast energy into its host galaxy, regulating star formation across intergalactic distances. NASA's Chandra X-ray Observatory and Hubble Space Telescope combined observations with the EHT to map the full energy outflow. In May 2022, the EHT team achieved another triumph by revealing the first image of Sagittarius A*, the black hole at the center of our Milky Way. Sagittarius A** is 4 million solar masses, over 1,000 times smaller and closer than M87 star. Because Sagittarius A** is smaller, plasma orbits its horizon in minutes rather than days, making data reconstruction far more difficult. Comparing M87* and Sagittarius A** proved that supermassive black holes exhibit identical event horizon physics regardless of their size. Whether 4 million or 6 billion solar masses, black holes obey universal relativistic laws. These images established black holes as real astronomical objects, transforming theoretical concepts into observational physics. They provided experimental laboratories for studying extreme gravity under maximum physical stress. Part 4 Summary. EHT images validated Einstein, mapped magnetic field lines, and confirmed universal black hole scaling. Part 5. The Next Frontier, Black Hole Movies and Orbital Telescopes. The success of the Event Horizon Telescope is only the beginning of black hole imaging technology. Astronomers are currently building the next-generation Event Horizon Telescope, or EHT. By adding new ground dishes in Greenland, France, and Argentina, EHT will increase image sharpness by a factor of 10. Instead of static photos, EHT will capture real-time 4K movies of black holes, tracking plasma swirling around event horizons. Scientists plan to launch space-based radio telescope satellites into Earth orbit. Space-based interferometry will expand the virtual telescope dish beyond the diameter of Earth into deep space. Orbital radio arrays will allow humanity to image sharp photon rings and resolve substructure near singularities. Future lunar radio arrays built on the far side of the Moon will probe cosmic black hole origins from the early universe. Studying black hole shadows helps theoretical physicists bridge general relativity with quantum mechanics. It provides crucial observational tests for string theory, Hawking radiation, and quantum gravity models. The first image of a black hole stands as one of humanity's greatest scientific achievements. It demonstrates that when humanity unites across borders, languages, and cultures, we can see the unseeable. From ancient human stargazers to modern global supercomputer arrays, our quest to understand the cosmos marches forward. Our home planet Earth rests safely in the quiet suburbs of the Milky Way, allowing us to study the universe in peace. Protecting our planet and fostering global scientific cooperation ensures future generations will continue exploring. Thank you for joining us on this exploration of the first black hole image and what it revealed. Keep looking up at the night sky, and never stop reaching for the frontiers of science. Protect our beautiful blue marble Earth, the ultimate oasis of life in the universe. Farewell, and see you on our next epic cosmic documentary journey. Until next time, keep exploring the wonders of deep space. May your curiosity always illuminate the cosmos. Clear skies, and happy stargazing. Peace and wonder across the universe.